Hello, my name is Dr. Jonathan Butsky. I'm not a medical doctor. Instead, I'm a robot doctor. Robots often need to be able to judge distances to objects, whether it's to avoid running into them or knowing how or where to pick them up. And if they don't do it right, bad things can happen. Did you know that back in 1999, the NASA Mars rover burned up in space? Because when calculating the height to start slowing down the rover, the engineers forgot to convert the values from imperial to metric units. So how does a robot keep track of distance? How does it know if it can fit into a space? A robot needs to be able to measure things, distances, size, angles, time, and other things. And we'll explore all that in this lesson. You'll need to rely on the math you already know, geometry, trigonometry, algebra, and some concepts from physics. But be prepared to take notes. Over the next 13 minutes, we'll discuss how robots measure. We'll look at how robots determine distances, how they measure angles, and how they measure time. In robotics, we use the metric system, also known as the SI units, for all of our measurements. You're probably used to measuring distances in feet. In the metric system, we use meters instead. A meter is 3.28 feet, so we can convert back and forth using this ratio. For example, I'm 6'2", about 6.17 feet tall. To get that translated to meters, we divide 6.17 by 3.28, and that gives us a length in meters. In this case, I'm about 1.9 meters tall. We typically use scientific notation to write large and small numbers. Let's take a closer look at what that means.
Scientific notation shows how many places the decimal point moves in the number. For example, 1 times 10 to the third power means that you would move the decimal point 3 places to the right, adding zeros as we go. Starting with 1, going to 10, then 100, finally 1000. So 1 times 10 to the third power is equal to 1000. Likewise, negative exponents mean we move the decimal to the left. Starting at 1 again, we go to 1/10th, 100th, and finally 1000th. 1 times 10 to the negative third power is equal to 1000th.
We use meters anytime the robot has to measure a distance or size. We measure how far objects are away from the robot in meters. We measure how far the robot has traveled in meters. And we describe the robot's dimensions in meters. When we talk about measuring things, however, meters aren't always the most convenient unit. Take, for example, measuring the thickness of a coin. I'm more likely to say it's 1 millimeter thick than I am to say it is 0.001 meters thick. A millimeter is a 1,000th of a meter. There are many standard prefixes we can use with metric units.
For small objects that you may be used to measuring in inches, we use the prefix centi for 1 times 10 to the negative 2 or 100th. Slightly smaller is the prefix milli, meaning 1 times 10 to the negative 3 or 1000th. Next comes micro, 1 times 10 to the negative 6 or 1/millionth, followed by nano for 1 times 10 to the negative 9th power or 1/billionth.
And believe it or not, there are nanorobots. They're named because they are very, very small. These robots are used in medicine, where they are injected into your veins, travel through your body to your heart, where they can monitor, clean, or fix damaged portions. For larger objects, there's another set of prefixes.
We use kilo to indicate 1 times 10 to the third power, or 1,000. Next comes mega, meaning 1 times 10 to the sixth, or 1 million. Then giga, at 1 times 10 to the ninth, or 1 billion. Then tera, meaning 1 times 10 to the 12th power, or 1 trillion. You may have heard these terms when talking about computers. For example, hard drives can be terabytes in size, meaning they hold 1 times 10 to the 12th bytes, or 1 trillion bytes.
Another example, self-driving cars measure speeds in kilometers per hour, that is, thousands of meters per hour. Besides measuring distances, robots often have to measure angles as well. For example, they may have to measure the angle of the robot's arm. In this case, we use radians rather than using degrees. You may already know that there are 360 degrees in a circle. There are also 2 pi radians in a circle as well. Just like we had a conversion factor from meters to feet, we can use these data points to get a conversion factor for radians. So if we have a 45-degree angle, we can convert that to radians by dividing by 180 and multiplying by pi. In this case, we get pi over 4 radians, which is the same as 45 degrees. Robots also need to be able to keep track of time, but that's the easy one. While many different time systems have been proposed over the years, the metric system uses the normal second as its base unit of time.
Speed can be thought of as a ratio of distance per time. That's another way of saying we have to consider the distance traveled compared with the amount of time it takes to get there. And that follows for the units as well. Our robot speeds are typically measured in meters per second, from a relatively slow ground robot to a self-driving car or a UAV. That's an unmanned aerial vehicle, sometimes known as a drone.
Another place that speeds show up is when a robot is trying to figure out how far away an object is. A common sensor for measuring this is the LiDAR. The LiDAR is like a radar, except for it uses infrared light instead of radio waves. LiDAR works by transmitting a pulse of light. Light in air travels 3 times 10 to the 8th meters per second. In other words, it travels 300 million meters every second, or 300,000 kilometers per second, which is the same as 186,000 miles per second. The sensor times how long it takes the light to travel out to an object, then bounce off and return back to the sensor. Since light travels very fast, the time for this trip is very short. In fact, it is usually measured in nanoseconds. Billionths of a second. There are 1 billion nanoseconds in a second, or 1 times 10 to the negative 9th seconds per nanosecond. Let's look at an example. Our robot is sitting outside looking at an obstacle. It uses its LiDAR to get a range to a nearby obstacle, in this case a tree. It gets a reflection back from the tree after 30 nanoseconds. That's our measurement of time. But how far away is the tree? We know that speed is equal to the distance divided by the time. We can rearrange this equation to show that distance is equal to speed multiplied by time. Since we know the speed of light is 3 times 10 to the 8th meters per second in air, and we were told that the time was 30 nanoseconds, we can multiply these two terms to get our distance. A nanosecond is 1 times 10 to the negative 9th power, and we can rearrange to get our units all together, and cancel out the seconds, then multiply the numbers, and simplify to get our total distance of 9 meters. We know that the light pulse traveled 9 meters. That's our total distance. However, that counts the trip from the robot to the tree and back again. So the robot is actually only half that distance from the tree, 9 divided by 2, which tells us the robot is 4.5 meters away, or about 15 feet from the tree. Now let's take a look at a simple robot arm. The arm has one joint and a fixed length arm with the end effector, or hand, at the tip. Since it only has one joint, the arm can place the end effector anywhere on a circle. If we know the object is 40 centimeters high, and we know that the arm is at an angle of 0.927 radians, which is about 53 degrees, how long does the arm have to be in order to reach the table? Let's start by drawing a picture of our scenario. Our object is on the table and is 40 centimeters above the ground. The robot is on the floor and its arm is making an angle of 0.927 radians with the floor. We use Greek letters to mark angles usually, so we will label that angle as theta, and x is our unknown length of the arm. We know this forms a right triangle with a height of 40 centimeters, an angle theta of 0.927 radians, and a hypotenuse of unknown length x. From trigonometry, we know that the sine of an angle is equal to the ratio of the opposite side divided by the hypotenuse. We can rearrange this equation to find our missing hypotenuse. We substitute in the numbers we have for the opposite side, and our angle theta, the sine of 0.927 radians, is equal to 0.8. We simplify and find that x is equal to 50 centimeters. This same process is used in real robots to determine their arm's position or to figure out what angle is required to reach a particular location. In this session, we have discussed some of the measurements robots use. We have discussed the units robots use to measure distance, angles, and time, as well as looking at how the robot uses that information during its operation. Now, get your pencils ready for this week's challenge questions. This week's challenge questions are: if we had a robot with a sonar sensor, how long would it take us to get the return pulse, or echo, from an object? We know the object is 10 meters away, and we know that the speed of sound in air is 343 meters per second. Again, if we know an object is 10 meters away, and the speed of sound is 343 meters per second, how long will it take to get the return echo? Your second challenge question, you need to figure out the height of the table. We have a robot arm that is 50 centimeters long and is at an angle of 0.5 radians. How high of a table can its end effector reach? Again, with an arm that is 50 centimeters long and an angle with the floor of 0.5 radians, what is the height of the table the robot can reach? I'm John the Robot Doctor. See you next time. Hey robot, can you measure me?
You can find these video lessons online at wqed.org/therobotdoctor.